So welcome back, Falcons. Last time we talked about all of these nitty-gritty pieces about the relationship between hypothesis tests and intervals. Now let's talk a little bit about what can go wrong. And obviously there's always going to be error involved. So when we perform a hypothesis test, we can make mistakes in two ways. We could say the null hypothesis is true, but we mistakenly reject it. So maybe we knew the null was to be true, but we said we're going to reject the null. We call that a type 1 error. Now, if the null hypothesis is false, but we failed to reject it, we would call this a false negative, and the other one would be called a false positive. All right, you've heard of those words. In statistics, we refer to a false positive as a type 1 error and a false negative as a type 2 error. So which type of error is more serious depends on the situation at hand. In other words, the gravity of the error is context dependent. If we are researching the efficacy of an extremely expensive drug to treat acne, a type 1 error suggests the drug is effective, is pretty expensive, but not so serious. If we are researching the efficacy of an extremely expensive drug to treat colon cancer, a type 1 error suggesting the drug is effective is pretty expensive and a much more serious mistake than just maybe it doesn't cure acne. Having said that, much research focuses on not making a type 1 error. So let's look at this chart. Let's go back to it's like a Punnett square. So either the null is true or the null is false. There is either a difference or there is no difference. So when we say it's a type 1 error, we're saying the null is true, but we rejected the null. So I'm calling this a false positive. Maybe you thought you were not sick, but you thought there was enough evidence, so you said you're sick, even though you weren't. A type 2 error is when the null is false, but you failed to reject it. I don't have an illness, but I think I'm okay. In context, you can see that this is kind of a problem sometimes. They're both issues that we try to ignore or get rid of, not ignore. So how often will a type 1 error occur? Well, since a type 1 error is rejecting a true null hypothesis, the probability of a type 1 error is our alpha level, because we are saying at some threshold alpha, what's the likelihood of getting that? Well, whatever you said it was. When the null is false and we reject it, our analysis is okay. So when the null is false and we reject it, we did what we were supposed to do. When the null is false and we fail to reject the null, we have made a type 2 error. So type 2 is when the null is false, but we fail to reject it. The letter B, or beta, this is beta, is used to represent the probability of a type 2 error. Now, it is extremely difficult to assess the value of beta because we have no way of knowing the actual value of the parameter. Thus, there's no single value for beta. There is a whole set of betas, one for each incorrect parameter value. And it's kind of this visual. I'm going to try my best to explain it. It'd be greater if it was animation, but this is from the book, so deal with me. This is what we call the power of a test. Here is how the situation might look. We are saying that the null hypothesis is here on this hypothesized distribution. If we were to reject the null, we would be in this alpha level. But what happens if the actual distribution is over here and the true p-value is here? Well, if the true p-value is there, we would reject the null. So we could always reduce the size of B by increasing A, right? You see, this blue area is where we would fail to reject the null. The red area is where we would reject the null. So if we reduce B, we shrink it down, we're going to increase A. So if we're increasing alpha, we're increasing the significance level, which means we are increasing a type 1 error. So the conflict between alpha and beta is unavoidable, but there is a way to reduce both. And I'll give you 3 guesses to figure out what they would be. But the first 2 don't count, okay? We've talked about this before. The only way to reduce both alpha and beta is to collect more data. Increase our sample size. Otherwise, we just wind up exchanging one kind of error for the other. Collecting more data increases the power of the test. Now, this word, I want you to think, what's the difference between binoculars and a telescope? They both look into distances, but it's a magnitude. So as we increase our sample size, we increase the power of the test. Because if I asked you, use binoculars to look at Mars, does Mars have any moons? If you're looking through binoculars, you're not going to see them. So you might say that there's no moons, even though you know that's true. Mars has a moon or 2. If you're looking with a research grade telescope, you're going to definitely see the moons because it has a higher magnitude or a larger power. So the power of a test is the probability of correctly rejecting a false null hypothesis. With a high power value, we have done a good job of investigating the situation, but there can be too much of a good thing. The power of a test is 1 minus beta. Beta is the probability that a test fails to reject a false hypothesis, while the power is the probability that a test correctly rejects a false null. So whenever a study fails to reject the null hypothesis, the test power must be considered. When calculating power, the assumption is the null hypothesis is false. The value of the power depends on the actual difference between the true value and the hypothesized value. The difference between the null hypothesis, P naught, and the true P is the effect size. So I'll go back here. If I know what we hypothesize to be true, and I know what the true value is, the effect size is the distance between those two. And by distance, I mean difference between those two. The power depends directly on effect size. The power depends directly on effect size. The larger the effect size, the easier it should be to see. So here, again, is our picture. Here is our null hypothesis. Here is our true p-value. Well, here also could be our true p-value. You can see that if we reject the null, there's plenty of places p could be. But that also gives you all of these areas underneath the curve, which we're calling the beta value. So here's the hypothesized distribution. Here is our effect size. Here's where might the true distribution be, but we also could have another one. And this is the hard part when we don't know everything. The greater the effect size, the greater the power, and the smaller the beta value. Because the greater the effect size is moving the curve further to the right and having less beta inside where I'm going to reject the null. So in essence, this is the takeaway. If you're going to put a star by this. The previous slide suggests that to reduce a type 1 error, we must automatically increase a type 2 error. But we can reduce both types of errors by making both curves narrower. How do we make curves narrower? We decrease the variability. How do we decrease the variability? We increase the sample size. Variability is the width. This is from the square root of p, q over n. So as n gets larger, our width gets smaller. So if we're going to try to reduce both type 1 and type 2 errors, this figure has means that are just as far apart as in the previous figure, but the sample sizes are larger. The standard deviations, thus, are smaller, and the error rates are reduced. So just for comparison, here's our original. We see our standard deviation. Here's our new one, and we see our standard deviation is smaller because we increased the effect size. So how much blue is here? That is our beta level. How much red is here is our alpha level. If we increase our sample size, we can see that both were shrunk down. So key thing is to be able to identify what a type 1 error and a type 2 error are. And then how do we reduce both a type 1 and type 2? Increase and. So that takes us to the end of chapter 21. Pretty straightforward. We'll do a couple problems and then we'll finish up unit 5. See ya.